All right, so thank you all for coming today. So I'm going to talk and introduce briefly the MATLAB program that is going to be, as I said at the beginning of class, 40% of your final grade. So the purpose of this program is to demonstrate a couple of key ideas from the class that are more difficult to show mathematically. So a lot of the times whenever we're talking about intermolecular forces, and this project does focus exclusively on intermolecular, no inner surface forces, we assume that everything is additive. We make certain simplifications in order to make it more mathematically straightforward. So this project looks a little bit at what something closer to a real system would look like. It's also designed to introduce a couple of key ideas to you about molecular modeling and simulation. In your textbook, I believe he says at some point that molecular modeling and simulation is sort of the gold standard for looking at how actual processes take place. There are a lot of wrong ways to do a simulation, but it's an increasingly important tool in looking at intermolecular and surface forces and how they drive things like self-assembly and large systems, protein folding, etc. Real fast, how many of you have not coded in MATLAB before or don't have any experience with MATLAB? Okay, cool. And then about how many of you would consider yourselves novices at coding in general? Okay, cool. So the idea is that this, I don't want this to be a super difficult programming problem because there are a lot of you who are new to coding. We'll have several sessions that'll help acquaint you with coding and the basics. And I'm going to try to go through some of those ideas today. Do all of you have MATLAB installed? You should be able to, if you don't, I think you can just Google UCSD MATLAB and you can download it for free through the library. And let me know if you have any questions with that. So what the program is in general is the idea is that it simulates using the forces that we've addressed in class, the Keesim, the Debye, and the London forces. It uses those to simulate small systems of molecules in 2 dimensions. So don't worry about the fact that it's in 2 dimensions. That's just for a simplified version of it, so you can easily see it on the screen. Use the same potentials and forces that you would in 3 dimensions. Don't try to derive your own for 2 dimensions. The only time that really comes up in a force law is in the Keesim interaction, where when it talks about the dipole-dipole interaction, it includes a phi angle, a torsional angle. That would be the into the board angle. That's always going to be 0 for us because we're in 2 dimensions. So that will simplify things a little bit. And in general, I would say in looking at the Keesim forces and looking at these interactions between dipoles at specific angles, your book has a really good treatment of that. So I'd really highly recommend going to the textbook. I believe it's chapter 4 on dipole-dipole interactions. It also uses a hard sphere radius just to simplify things. So this is a specialized system. If you're doing a normal simulation, generally speaking, you would do everything in terms of just a Leonard-Jones potential, and then for dipole interactions, you would do a quantum mechanical calculation in something like Gaussian or Orca. You would get partial charges on each atom, and then you would just have Coulombic effects. But since we're in intermolecular and surface forces class, and these are the forces we've talked about, this is what we're doing. All right, cool. So real fast, there are 2 big ideas from modeling that I'd like to see you guys at least introduced to in this course. And this program incorporates both of these ideas. So one is molecular dynamics. So the idea behind a molecular dynamic simulation, one thing that I like to think about whenever I think about molecular dynamics is there's this idea called Laplace's demon. So basically this mathematician, Laplace, had this idea that if you knew the positions and momentums of all particles in the universe at a specific point in time, you could basically integrate forward in time and know everything that's going to happen in the future. There's a question about whether or not that would actually be true on the quantum mechanical level, but in molecular dynamics, we basically assume that this is true. So we set up a system of atoms in an initial position. We calculate the forces on each individual atom at a specific point in time, and we advance a very small portion in time ahead. Typically, it's on the order of femtoseconds. That's about 10 to the negative 15 seconds, which is really, really short. It's typically limited by the shortest movement, like bond vibration in your system. That'll a lot of time be a CH bond, so about 10 to the negative 15. But it just basically takes all of your intermolecular forces, calculates the forces. You can use Newton's third law to then calculate the acceleration and advance through time. So if you're interested in molecular dynamics, this is the velocity Verlet scheme for integration, just these 4 lines right here. So this is what advances your program through time. It's used really commonly in molecular dynamics simulations. It's very stable, but also not too computationally expensive. And then below that, there's a bunch of stuff on collisions that I should have put in a separate function, but that's fine. So a couple of things about molecular dynamics. I would say molecular dynamics is really interesting whenever you want to actually watch how molecules and atoms would move for real. If you're trying to look at a transition state, how a protein folds whenever it interacts with something else, molecular dynamics is going to be the best way to do that. The downside of molecular dynamics is that because you're moving on a femtosecond timescale, traditional molecular dynamics oftentimes only gets into the nanosecond regime. In terms of the amount of time you can actually simulate. To put that in perspective, in 1 nanosecond, time travels 1 foot. So it's not a lot to actually do, but computation is improving pretty rapidly. There are different ways to do some like adaptive sampling where you look at only the most interesting timescales to sort of extend your frame. And people have been making specialized computers for molecular dynamics in addition, so people have actually been able to simulate up to milliseconds now. So that's on the time scales that Darren was talking about today for self-assembly and things like that. So it's an increasingly powerful idea. Just wanted to introduce that to you. The other idea that I'd like to introduce is this idea of Monte Carlo. So while molecular dynamics was all it was all time reversible, everything was predetermined, you were just integrating things. Monte Carlo, it's named after a casino. There's some element of randomness to it. So basically what Monte Carlo looks at is it just tries to make a random move within a certain boundary. So what I use this for is the dipoles in your code. In this function, generate new dipoles, that's where I implement the Monte Carlo portion of the code. It just tries to move every dipole 5 degrees, one direction or another, calculates the new energy of that state. If it's more energetically favorable, awesome, it automatically accepts it. If not, it uses a Boltzmann distribution. It's e to the negative energy over kT of the new state over the old state to assign a probability that it will accept that move. This is what we use for the dipoles. And so this is a really similar idea to, in general, how you go from the individual Keesom interactions, because remember, your dipoles are moving around all the time. So we end up doing an angle average based on the Boltzmann distribution. This is trying to replicate the idea of going from individual dipole-dipole interactions to the angle averaged over time, where it favors certain interactions, but it explores all of them. So that's the idea behind that. So let's look at the actual project itself. So you all should have all of the files for this. You don't have to code any of the molecular dynamics or Monte Carlo stuff. That's all coded for you. So the way to run the program is from this function, GUI3, that stands for Graphical User Interface, and then it was my third pass at doing it. So all you have to do is go to this function and hit. And it should give you this screen. On your left here, you have a lot of user inputs, a number of atoms, and then a lot of ideas that we've explored, that we've talked about in terms of intermolecular forces, things like the polarizability, the dipole, ionization potential. All these are also given with the units that you need to input them with. So generally speaking, I think that the questions only refer to water, and I think in one maybe neon. But most of the time, just using either the initially input values or the values for water are going to get you through. And then whenever you need to change between them, there are 4 sections to this. There's 2 static dipoles, many static dipoles, 2 moving dipoles, and many moving dipoles. You can select each of those at the top here. And then if you need to change something in one of those individual, it's underneath this heading push button 1 callback. This is the function that executes whenever you hit go. Case 1 is the first one. That's 2 static dipoles. Case 2 is the next one, 2 moving dipoles, et cetera, et cetera. Whenever you hit it, it should run, and it'll run a simulation for you. You can observe that. I ask you for a couple of plots and I believe 1 screenshot. So just put together a Word file at the end with your answers to the problem and any graphs or screenshots that you generated during the making of it. That helps demonstrate. Cool? All right. Yeah.
After opening the zip file, it seems to be corrupted.
It's corrupted?
Yeah, me too. I got that. It was fine.
You have to open up via Google Drive for some reason.
You have to open up the what?
You have to, for some reason you can't download it. You have to like open it up through Google Drive.
Oh. Okay.
Have you tried putting it in like a S folder?
It should be already in a zip folder. I'll try to put another folder available directly for download from the course page, and hopefully that can help. So it's not on Google Drive and won't do anything weird. Let me know if you guys continue having problems once we do that. Sound good? Okay. Cool. Real fast, I want to talk to you guys a little bit about MATLAB and the code itself. So for those of you that haven't done MATLAB, which is, it looks like about half the class, I can acquaint you real fast. So for those of you who have done MATLAB before, just some quick refreshers. These are the things that I forgot because I mostly code in Python. So MATLAB runs, unlike Python, it's not on an indentation-based system. Everything is some statement, an if statement, blah, 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 and then end statement. Everything runs in between a statement and an end. Don't worry if you're not following this. If you're new to MATLAB, we'll do a slower version of this as well. But for those of you who do know this, just real fast, indices start at 1 for all of your lists, not at 0. Semicolons aren't necessary, but they do suppress output. So if I can run my program test here with just I equals 1. If I run that, it outputs I equals 1. If I put a semicolon, it doesn't. So that's actually really helpful in being able to check your program as you run through. You can put statements. You can just delete the semicolon and put a pause, and the program will run there, and until you hit enter, it'll pause and won't continue executing, so you can see what your values are at individual times. All right, so if you are good at MATLAB, if you're well acquainted with MATLAB right now, it's a good time to check your email. So I'm going to talk about a couple of key ideas in programming that you'll need to know in order to complete this project. So I want to talk about are variables, lists and matrices, if statements, list iteration, and functions. And those 5 concepts should be able to give you a good introduction to programming ideas and also get you through this project. So A variable is similar to a variable in algebra. It holds a predetermined value. In MATLAB, this value is typically a number, but it could also be something like a string. So the way you define a variable is you give it a name, something like I, or I could just call it variable. I can set it equal to a number. So variable equals 0. I can run this, and it shows me that, yes, variable is equal to 0. So this could be a user input thing. So it takes all of the user inputs from the program for that user interface and sets alpha equals whatever you put in there, and the number of molecules equals the number of atoms that you put in there, etc. You can then manipulate your variables. So I say variable equals 1. Now I can say variable equals variable times 2. And output variable equals, oh, did I misspell? Yeah, I misspelled one of them. Variable equals 2 at the end. So you can manipulate variables. They store values that you can manipulate throughout in order to get to a final answer. And as I said before, you can print the output by you can just write variable like this. With no semicolon after that, and that'll output what the value of the variable at that point in time is. The next thing I wanted to talk about is our lists and matrices. So what a list is it's just a bunch of variables but that are related to each other that you set up in a row. So I could define some list equals, and the way that I like to define my list in MATLAB is there's this function zeros and then the length of the list. So 0 is 5. Actually, that gives a 5 by 5 matrix, so I'll do 5, 1. So this creates a list of 5 values, and it sets them all equal to 0 at the beginning. If I want to access an individual portion of that list, what I can do is refer to what's called the index. So list, so I say I want the third value in the list. I say list 3, print that out, and that's 0. If I want to set the third index equal to something else, like 5, list 3 equals 5. And you can see the third value has been changed to 5. Matrices are just a scaling up of this idea in 2 dimensions. So in a lot of programming languages, the way to think about a matrix is a list of lists. So you have a list, and then each list contains another list, sort of in another direction. MATLAB is a really matrix-based language, and so you can actually access everything in a matrix using the format that you usually describe elements of a matrix in linear algebra. So if I just define a matrix, so if you just put in one parameter in zeros, it makes just a 5 by 5 matrix here. So everything's 0, 5 by 5 matrix. If I want to access the element in the second row and the fourth column, I would say 2, 4. And that's just the standard way of describing elements in a matrix from linear algebra. Print list. Now we've set the element in the second row and fourth column equal to 5. So this is really useful whenever you're doing, say, keeping track of all of the forces on all of your atoms. So you'll probably want a n by 2 matrix where n is the number of atoms, so the force on each individual atom, and then the x component and the y component broken down. So that's a good way to keep track. For your W's, for your energies, you probably want just an n by 1, so where it keeps track of, for every individual atom, what its particular energy is in its state. Making sense? This might be a little fast if you're completely new to programming. Don't worry, we'll have more sessions that are slower with more examples in the future. The next thing I want to touch on really quickly is if statements. So this is getting into controlling, yeah?
Could you tell me what is workspace then? Why do we use
So the workspace that'll show you what the values at the end of your program or wherever you are in the program are. So it's saying answer, whatever that is 0. I is equal to 1 at the end of the program. List is currently a 5x5 matrix of what are called doubles. Doubles are just numbers with decimal places in them. So that's what the workspace keeps track of. Then your command window, your output window, is where it prints out anything that's not suppressed by a semicolon. Cool. All right, so if statements are how you control what your program actually executes. So say I want to print out something only if the user input is, so we've got alpha. Let's define alpha equals 1 here. So we're only going to print it if alpha is even. So I'm going to write what's called an if statement here. And so now I have to put a statement that if it's true, the next statement will execute, or whatever's between this if and the end, all that will execute. If it's not true, it'll just ignore it completely. So that's a way to control what executes and what doesn't execute in your program. So for even odd, this function is really nice, mod. So this is just like an old school, before you knew how to do fractions, this gives back what the remainder of what one number divided by another number is. So 5 mod 2 has a remainder of 1, it gives back 1. 4 mod 2 divides evenly, it gives back 0. So all you really need to know for this example is that anything mod 2, if it's even, it'll give back 0. If it's odd, it gives back 1. So let's say mod alpha 2. So we're only going to print it out if it is equal to 0. Now notice that for these expressions, I write a double equal sign. So that's not setting it equal to 0. That's asking, is it equal to 0? So that'll return true if that value is equal to 0. It'll return false if it's not, and it won't execute. Other good ones to know, greater than, less than, greater than or equal to, less than or equal to, and in MATLAB is not equal to is a tilde equal sign. So those are the basic ones that you're generally going to see in if statements. So we'll say mod alpha equals 0, print out alpha. Since it's an odd number, it didn't execute that and print that out. If I set alpha equal to 2 though, we can see it does execute in that case. So it's a way to control the flow of your program. You can extend this further. So let's say if it's an even number, I still want to print it out, but I want to print the next even number above it. So then I can add an else statement. So if this if statement doesn't execute, then this else statement will. All right, so if it's an odd number, I'm going to want to print out alpha plus 1. So now let's try that again. So at 1, it prints out 2. So it executed this else statement because this if statement was not true. And then if it's 2, it executes this first statement still and prints out just what alpha is originally. So that's another level of control you have over what executes and what doesn't in your program. Really quickly, I'd like to address list iteration. So you've got a list full of lots and lots of variables, and you want to access them all. You probably don't want to just type out f of 1, f of 2 equals f of 3 and go through item by item. So what you can do to make this a lot faster is use, in particular, what's called a for loop. So what I do is I define for here. Usually use some sort of counter variable. So a lot of times that'll be an I or a J if you've already used I. So for I equals your starting value. So for a list, typically that'll be 1 because you want to start at the first value. And then your ending value. So if I've got a list of length 5, then what I'll typically do is there's a function length of list, and then I'll just give back the total number of elements in your list. And so then let's say that I want to set list of index I equal to I. So what this would do is it sets whatever the value is at that index equal to the number of the index. So it should just give us 1, 2, 3, 4, 5. All right, so I starts at 1. It'll increase by a value of 1 every time we go through this until it gets to the value of length list. So that's a good way to go through every item in a list that you have and change all of them or add them all together, manipulate them in a certain way. So if I do this, then I'll end up with 1, 2, 3, 4, 5, something like that. If I wanted to I could do the same thing, but have them all squared. Sorry, use Python. And then it just gives you the square of the index values throughout. So that's a good way to go through and manipulate all of your list elements. I'm going to skip while statements there. The last thing that I want to touch on really, really fast is the idea of a function. So I've used a couple of functions throughout, things like the length function, the mod function. So what that is you give some sort of input, like a list for the length function. I'm putting in length list. I'm giving some input in, and then it gives me it does some calculation on it, and it gives me something out. And you can actually define your own functions for things that you're doing repeatedly, like calculating the Keesim energy or the Debye forces, all of these things. So I've actually pre-written several functions for you for the, this is the key, for the different things that you'll need to calculate, like Keesim, Debye, and London. And so you'll just have to fill out the portion of that in between. But what I want to show you about functions is that on the right here, it's got the name of your function. So in this case, it's the Keesim force. And it's got these variables in parentheses right here. So these are the values that you're going to give the function. It gives in x, and I've got comments here describing what each of these are. X is a matrix with all of the position values for all of your atoms or molecules. U is the strength of your dipole moment. Dipoles is the current dipole angles that all of these are held at. And J is the index in X that you're calculating the energy and force on at this moment. So these are the values that you have to work with. You can work with these, manipulate these, use these values to calculate what you need. And on the left here in these brackets are 3 values, W, F, and in this one it's got W norm. These are the things that at the end of your function you're going to give back out to the rest of your program. So it'll return, you need to return some list W of the total dipole energy, some F resulting in your forces. These are the things you need to calculate and give back out at the end of your function. All right, so that was a really fast overview of the general concepts. I included, I think, a MATLAB resource guide that can help you, and we'll have several sessions that'll go slower with more examples on the concepts you need to know in order to finish this project. So I want all of you to get the full 40 points on this. Hope that helped some, and see you at office hours.
When I download MATLAB, it's gonna come the file below the things that you said. How I can find it.